Vande Mataram everyone and welcome to the channel. If you are a third year chemical engineering student and struggling with the chemical process control, then this video is just for you. In this session, we will break down the things like transfer function, first order system, the responses of the first order system like a step response, impulse response, also mixing process, the response transfer function for a mixing process, and mercury bulb thermometer transfer function for it, and also the response equation for the mercury bulb thermometer. Also we will deal the previous pure capacity for capacity system, also feedback control, and we will deal with I have also included the previous year questions with the answers, and it will definitely help you to in your ISC examinations and also your end semester exams. So stay with me till the end of the video and let's make the process control super easy. So let's start with the first question. So define the transfer function for a first order system and also the transfer function for a single liquid level tank. So here the definition of a transfer function. The transfer function, not a definition of transfer function, it's a definition of a first order system. So first order system is whose output is in a whose outputs differential is first order differential. So this is the equation. Then we will deal with the characteristics of the first order system. So their capacity to store the material, energy, and momentum. So the first order system is it's one who store the material, energy, and momentum. So for example, the a single liquid level tank is there, so it store the material, it's also store the energy, and here transfer of that is the flow rate Fi, and output flow rate is F naught. So it's the momentum transfer is there. So it's first order system. So also we will deal with now. Let's start actual video. Actual video. So these notes are prepared by me. So it's a first order system, that is a single liquid level tank, and let's make some assumptions here. Constant density is there, density of the fluid. It means it's incompressible fluid, and no chemical reaction is happening in the process. So in the, not a process in this system. So, so here. So now the material balance. First, we will take the material balance. So I will define the system first. So here it's the density, it's input flow rate, it's output flow rate, and here the wall is there. That is the resistance for a flow. A is the total internal area, that is a cross sectional area, and it's the height of the liquid level tank. So material balance for an unsteady state condition. For unsteady state condition, that is the input minus output and accumulation. So for input here, rho into flow rate. So we are going to deal with here, that is the rho. So equation units for a rho is uh, kg per meter cube, and into the unit for flow rate is meter cube per second. So meter cube get cancel, and kg per second is our unit. And here also the same unit is there. So that's why input minus output is equal to accumulation is there. So rho get cancelled. Yeah, and we get this system. So we call the first equation is there. Then for a steady state condition, we know the rate of transportation is a constant. That is, the input is equal to output, and there is no accumulation in a steady state process. So when the input rate is equal to output rate, then we can say that the system is in a steady state condition. So I repeat, when Qi is equal to Q naught, then and only then we will call the steady state condition. So here Q at a steady state, so that's why I here write the S. It indicates the steady state condition. This is the second equation. Now we will subtract equation 2 from equation 1 here. So Qi of a t minus Q at a steady state, and this. So the this so we know this equation. We have to know this equation. So instead of this, I am writing Qi of t here, capital Qi of t, and here capital Q naught of a t. And here one thing is there. We know the differentiation of a constant is differentiation of constant is 0. So if the input rate is equal to output rate, then there is no change in height. That's why here I am writing here h of t minus h at steady state. So h at a steady state is 0. So that's why I am writing here capital H of t. So, and also we know if I want to find the output flow rate, then I have to divide resistance by height, then I will get the output flow rate. So that's why the Q naught is equals to H upon R, and I am writing it in the form of capital letters. And if I do the Laplace transform here, so capital Q of S, that is the output, is equal to capital HS by R. So here I arrange and also I do the Laplace transform for equation 3 here. Take the Laplace transform of equation 3, and this is the Laplace. We know the Laplace of a differential equation is S into HS. So this is the Laplace transform. Now I put the value of Q not S from here. So I put here, and I am writing the transfer function in the form of input flow rate. So that's why the QIS, I arrange the things here, you can understand. And of A into R is tau. So I put A into R as a tau. That's why A into R, I put tau into S plus 1 upon R. So its output minus input is equal to capital Y of S, X of S is equal to H S by Q naught QIS is equal to R upon tau S plus 1. So I put directly instead of Q naught S here, I put HS by R. If I am going to put instead of HS here, HS that is R into Q naught S, so the my case 2 is there for this, and in case 2 I got this equation. So here one thing you can realize that here is R is present and 1 is present. So why this is there? Because of single input we are dealing with a multiple input and multiple output. That is MIMO system. So this is if I am going to take a ratio of input flow rate and output flow rate, then it become 1 here. And if I am taking the ratio of input flow rate and height, then R comes in a picture here. That's the question. So now we will deal with the step response for step response. So step response is this is the graphical presentation of a step response. Here from A to B, it's a steady state condition. Then small change I introduce, that is I called it as a step response. So small step change is there, and my system from B to C is there, and from B to C is the magnitude, that is I have mentioned here. So B to C is a magnitude, and A to B is the steady state condition. So I take the Laplace transform for this, that is f of t is the input, my input is there. So f of t is equal to a, that is from 0 to a here, that is the magnitude, and a, and I take the Laplace of a constant, that is constant upon s, so the Laplace is a by s. So now we know the response equation is in the form of output. So here I am going to put the output. So we know we have already derived step response for a single first order system. So here is the step response, first order system. So instead of qi of s, that is here as, so it's from denominator to the numerator a by s. And if I put a is unity, that is 1, then it becomes like this equation. So now I have to take inverse Laplace transform. For inverse Laplace transform, here I have to use the partial fraction method. So C1 and C2 I have introduced here. So I put for this denominator term in left side comes in the right side as a multiply. So 1 by tau is equal to C1, and this is the equation. So now I put Cs is equal to minus 1 by tau, and I got the C2 is minus 1, and C1 as 1. So now after this I am going to put the values of a C1 and a C2 here, that is 1 and minus 1 is there, and I take the inverse Laplace. So we know the Laplace of 1. Laplace of 1 is 1 by s. So it comes as a 1 by s, and Laplace of this, inverse Laplace of this is e raised to minus t by tau. So here e raised to minus t by tau is there. So my equation, that is small y of t is equal to q of t is equal to m into, so here instead of 1 I am putting m as a magnitude, I can put here as a also. So for your reference, 1 minus e raised to minus t by 2. And whatever equations I am going to put here are from Stephanopoulos book. So you can refer it also. 173 page number is there. Now for impulse change. So for first order system, the impulse change is like slightly impulse, then again at a steady state condition. So this is the graphical representation of the impulse function. And this is the, so here I will explain why, how it comes in a picture. So you can see that from 0 to b, from here is also 0, from 0, that is t. So the, if my output is a 0, that is 0, so it's t becomes less than 0, so the value is less than 0. If my output is a, that is a here, then my response exists in a 0 to b, that is 0 to b, so t in between a to b. And for a 0, then again it's 0, so it's t is greater than b. So you can, I can say that. So here x of t, that is my input, is equals to a dou t. So I take Laplace here. The Laplace is capital S. Capital S, x of s is equal to 1, and a, not a 1, is a. So it's the magnitude. I already mentioned 0 to 1 is the magnitude. So now we know the transfer function. The transfer function is that g of s is equal to y of s upon x of s. So that's q naught of s upon qi of s. That is q naught s means output upon Laplace of output upon Laplace of input. So it's 1 upon tau s plus 1. So also the same procedure which we have done in a previous example, we have to do it for this also. So put here a, so this is in a denominator, it comes in a numerator like this. So now it becomes like this, a into, so I take tau as a common here from here, for to get the standard equation, and I got this equation here. A by tau is there, a by tau is there. So my q2 and this equation I got here, you can see that. And I take inverse Laplace of it, and the inverse Laplace is a upon tau e raised to minus t by tau. So now let's deal with the mixing process. It can become a very important is there, very important question is there for a mixing process. So for any, if you want to find the transfer function for any system, first order system, first you have to draw the figure, then you have to do the assumptions, then material balance, energy balance and momentum balance equations, then at a unsteady state, then steady state, and then subtract equation 1 from 2, that is from unsteady state to steady state condition. So here I have done the component balance. Here is the same, that is a q, and here q is output, and this is the mixing tank, but there is no chemical reaction. Uniform concentration of the component is there, and volume hold up is constant. So here it mentions that volume hold up is constant, means the H is not going to change. That's why we can say that input rate and output rate are constant. So that's why here Q and Q, not I have not mentioned here QI and Q naught. That's because of the both are same. That's why the volume holdup is constant. So let's component balance is there. Let's take component balance. So Q into component, that is Q into X of t minus Q into Y of t is equals to V into dy of t upon dt. And at a steady state condition it becomes 0. And also we know the component balance in component, so input minus output minus the rate of disappearance is equals to accumulation. But here is no chemical reaction is there, that's why the rate of disappearance is 0. And also it's in unsteady state condition, this is the equation. And at a steady state condition, the accumulation is also 0, so that's why here 0 is present. So this is the equation. Now as usual, equation we subtract equation 2 from 1, this equation comes in picture. Then I, instead of this and this, I write capital T and capital Y here. This q is in a multiplication, it comes in a denominator at the right hand side. So I am going to write it in the form of x of s. So I take the Laplace transform here. So x of s is equals to v by q s into, we know that the Laplace of differential equation is s into differential equation. So s into y of s plus here y minus y of s, y of t. After the Laplace transform, it comes as a y of s, and from minus y of s, it comes as a plus y of s here. Now I take v by q as a tau. So I put the things here, and I got the transfer function as a 1 upon tau s plus 1. So whether you are going to take a component balance or overall material balance or energy balance or any system, if your system is in a first order system, your transfer function is always constant or the same, that is 1 upon tau s plus 1. So that's I'm trying to say. Now the in every year at end semester and I in semester exams, one question you have already seen that the mercury bulb thermometer. So the mercury bulb thermometer is also a single first order system. So let's derive the transfer function for the mercury bulb thermometer. So this is the mercury bulb thermometer. That is, the mercury bulb thermometer is the thermometer works on a expansion, volume expansion of a mercury. So here is the input, that is x of t, x of t, the change in a temperature of surrounding, and here the expansion of the mercury is there, and it's a transfer function. So let's do some assumptions. The resistance of the glass is zero, no resistance offered by the glass, no glass expansion of the mercury bulb thermometer is there, and only we will consider the only convective heat transfer, not a conductive heat transfer. So this heat transfer between these the walls is zero or negligible. We will only deal with this transfer only, this this transfer, this is transfer considered, and uniform temperature of the mercury bulb mercury bulb. So let's take the energy balance here. So for energy balance, we know the input is equal to output. So here HA delta T is equals to MCP delta T. So I put all the equations here. HA is constant. The temperature, I have mentioned that this is the input temperature and this is the temperature shown by the thermometer. So put here, and I put the equation also here for unsteady state condition, for unsteady state. Now I am going to write it for steady state condition. So accumulation is zero. So that's why MCP delta T term comes becomes zero. So usually, as usual, we will deal with the I minus equation one. We will subtract equation two from equation one. So my equation, instead of this and this, I am writing uh, here. I am writing capital terms, not yes, capital terms I am going to write. So it comes as a this, and instead of mcp upon ha, I put tau is tau there, and here we you can say that the m into cp is the capacitance, and a into h is the resistance offered to the system. So now take the Laplace transform of this, and the Laplace transform is here. So we can say that the Laplace of differential equation is the s into that constant term. So tau into s into y of s. So I put minus y of s is here. So it become plus y of s. And again the equation comes same. So whether your system is different, but all this, if your system is a first order system, then your transfer function is always same. That is 1 upon tau s plus 1. Now we are at coming to the end. In 2 to 3 minutes, we will conclude our session. So it's very important, the pure capacity system for 5 to 6 marks. It can be come for your exam. So let's do it. So the pure capacity system means the resistance is zero. So there is no resistance is in your system. So as we know that we are here introduce one resistance. So for this it's become zero, it's become zero. So I am writing here q I, so same material balance equation I am writing here. So for if my resistance is zero, then my input is equals to output. It's always it can become as input is equal to output. So here yes, so this term is become, no, that it's not the case. For I am going to unsteady state condition, I have write the material balance. For steady state condition, this is the, then input minus output is there. So here my this term is going to zero, it's zero. That's why that's I already mentioned that resistance is zero and all the things. So equation becomes this, and if the resistance is zero, then for the pure capacity system is 1 by s. So now the at the end we will deal with the feedback control. So it's very important, and I again mentioned that the all the things I am going to explain, I have already mentioned that all the things are from the chemical process control book by the Stephanopoulos, Dr. Stephanopoulos. So here is the one system, that is the heating tank system I have mentioned here. And for the heating, one heating steam, one steam, that is the FST, I have provided, and FIT is the input, TI is the temperature, input temperature, this is the agitator, FI is the output, and T is the output temperature. To measure the temperature, here is one line is there, this line is there. So let's, sorry, uh, this here, yes, it's, so hmm. It's from here one thermocouple is there. So now it's ready. So here we will first measure the thermocouple from here. The thermocouple will measure the temperature of the system here, system temperature. Then it will send the signal to the here, and TD is my desired temperature. Desired temperature. So error means what? Error means E is equal to my dt minus the difference between dt and T. T means the temperature of the system, and here E. Then error signal comes to the controller, and controller send the signals to the my pneumatic control valve. And according to the control signals from the controller, my pneumatic valve will send the signal to the valve, and it will regulate the my steam flow rate, that is the FST here. Also the same system, this is this feedback control system is for uh, uh, on, heating tank system. Now the same system is for the distillation column. So here one distillation column is there, and this is the bottom section, that is the raffinate, not a raffinate, it's a feed to the system, that is the column. And it's the condenser is there, a reflux drum is there, and I have to measure, or I have to control my xt, that is the distillate concentration, that is the distillate I have to control. So to control xd, there is only one way is there to regulate the reflux. To control the reflux, I have to put one control system here, and I am going to put the feedback control system for this. So here a composition analyzer. So which can composition, if I want the purity is 0. I want purity is 98 or 99.43%. So my composition analyzer detect it. If it is not there, if desired is, I am putting desired composition here, that is XDD, and here the XD is minus, and then error signal is in a composition controller, and it will put the signal to the control valve, and control valve will regulate the reflux ratio, and it's sent to the here. So this is my feedback control. And these are the, if you have any doubt in this all the session, you can message me, you can mail me all the doubts, all the suggestions, because I am ready for the suggestions, I am open for the suggestions, because it's my first video. So thank you for joining me, and I again mention that it will really help you for